Hello everyone, I'm Kezhao Huang from Tsinghua University. It is my pleasure to present our work. This is a collaborative work from Tsinghua University, Alibaba Group, the University of Seoul, and North Carolina State University. In this work, we find out and bridge the gaps in current graph neural network performance optimizations. First, I want to introduce what is graph neural network. GNN, short for graph neural network, is a combination of graph data and deep neural network. Graph data can represent most kinds of real-world data, while neural network greatly improves the accuracy of the models. Therefore, GNN has been widely adopted in many areas, including social network, recommendation system, and molecular structure prediction. Here are the important concepts of GNN and the basic components. Nodes and edges build up the graph structure. Nodes represent the entities, with vectors as the features of the nodes. Edges represent the relationship between entities. Graph operations are performed with graph structure to encode the graph structure into the node features. Neural operations are performed to transform and activate the node features. These operations build up the computation graph. The graph and neural operations are in interleaved pattern on the computation graph. The slides have three parts. In the first part, I will introduce the performance gaps we observed in the existing GNN frameworks. We summarized them into 5 observations. Then in the second part, 4 optimizations to bridge the gaps are introduced. As last, I will show the experimental results to demonstrate the effect of our optimization. The following slides will introduce the 5 observations we have in the existing frameworks. 2 of them are related to graph. 3 of them are due to combination of graph and neural operations. To evaluate the existing frameworks, we picked up DGL and PYG, 2 popular GNN frameworks. The evaluation is carried out on NVIDIA GPU, which is the most popular hardware for machine learning. We used the datasets in Open Graph Benchmark, the benchmark for graph machine learning research. These datasets are closer to realistic problems, with more nodes and edges than the toy datasets like Quora and PubMed. Moreover, it includes the graphs from different fields. In this presentation, we only introduce DGL in detail, which has more efficient design and implementation. To find more about PYG, please refer to our paper. The first observation is about locality. DGL has poor locality with average L2 cache miss rate at 54%. In DGL, the graph operations are performed in node-wise parallelism. The conceptual graph operation is illustrated below. In DGL implementation, the threads will firstly fetch from the feature matrices, like this. Then they will reduce the fetched features to the destination node features. The memory access is following graph structure, which is irregular and leads to poor locality. This figure shows the L2 cache miss rate in different datasets. 2 bars indicate the 2 different implementations in DGL. We can find out that on most datasets, the implementation both have poor locality, with L2 cache miss rate higher than 50%. The second observation is about workload balance. As GPU is using large number of threads to compute, workload balance is an important factor for overall performance. However, in DGL, during 30.9% of the execution time, the device is under utilization with inactive SMs. The workload of graph operation for every center node is determined by the number of its neighbors. However, irregularity of graph structure leads to large variance in neighbor number and results in workload imbalance. The 2 figures shows the execution time of every streaming multiprocessor. In graph operations, severe workload imbalance is observed. The third observation is about the number of function calls. In DGL, intensive function calls are made to perform the graph and neural operations. They result in large amount of memory access and kernel launch overhead, which then lead to 52% performance slowdown. GNN is a combination of graph and neural operations. On the computation graph, graph operations and neural operations are in interleaved pattern. Though neural operations are dense and regular, the graph operations have unpredictable memory access and complex dependence, making kernel fusion on the GNN computation graph challenging. We use GAT, short for Graph Attention Network, to demonstrate this observation. The formula is a computation for a GAT layer. The particular computation is edge softmax, which will normalize the edge value among neighbor nodes. The animation shows the computation, with the code snippet showing the implementation in DGL. The first step is to add source and destination attention values onto the edges and perform the activation. Then is the edge value reduced to the center node to get the sum. After that, the sum is broadcast to edges to normalize the edge value. At last, the normalized edge value is used in feature aggregation. We can find that the data is transferred between nodes and edges, which leads to complex dependence. And there are in total 7 kernels to perform a single GNN layer. This slide shows how DGL tackles the dependence between stages and explains why DGL needs so many kernels to build up a simple GNN layer. First, after each thread got the computation results, they will store them to the global memory. Then DGL will launch a new kernel to unload from the global memory. The visit of global memory leads to large overhead, and DGL makes use of global memory to share data globally in order to meet the dependence between stages. This is a coarse-grained way because the data only needs to be shared within each thread block in this example. The fourth observation is a redundancy in the frameworks when the neural operations are performed by the graph structures. In DGL implementation, the redundant data movement and computation have 30% overhead. First, I want to introduce how we perform the neural operations by graph structure. Let us start from one of the most popular neural network structures, LSTM cell. A basic LSTM cell consists of the dense operations to transform the features. It is shown in blue parts. And there are also element-wise operations that activate the features. They are shown in yellow parts. LSTM has multiple steps of cells, as illustrated below. Graph structure is used to perform LSTM in GNN. Neighbors of the center node will feed their feature into LSTM, and the output features are used to update center node's features. Here we introduce the implementation in DGL. We use a Johnson matrix to represent the graph structure. The first step of DGL is moving data according to the neighbor distribution, and will generate the dense matrix for center nodes. In the second step, DGL will fit the dense matrix into the LSTM cells. To perform the neural operation by graph structure, DGL will gather the neighbor feature. The data movement is costly. And in LSTM, we can find that though node number 4 is a common neighbor, the transformation is still performed twice, which is redundant. According to our profiling, The data movement is 9.1% of the total execution time on average, while redundant transformation is 22%. In the last observation, we explore how frameworks tackle different situations. The most particular is the feature length. Feature length is critical in DGL performance. Little changes can lead to large performance drop. The neural operations in GNN will change the length of node features. Therefore, different layers GNN is trained with node features of various lengths. The figure shows the performance of the graph structure in DGL with different feature lengths. At some feature lengths, such as 64 or 128, the performance is good. However, when the length has slight change, the performance has a rapid drop. With the observations of performance gaps in existing frameworks, we use 4 optimizations to bridge the gaps. The first optimization is about graph structure. It reconstructs the graph structure to reschedule the computing tasks in order to improve locality and workload balance. Due to the irregularity of graphs, the graph operations suffer from locality and workload balance, as mentioned in observation 1 and 2. The first optimization is to reconstruct the graph to reschedule the tasks. Locality-aware reordering is to improve the locality, and neighbor grouping is to solve the problem of workload imbalance. Common neighbors between nodes can benefit locality, as illustrated below. Node 1 and node number 2 shares common neighbor node number 4. When performing the graph's operation, feature of node number 4 can be reused in cache as marked in green color. But if not closely computed, cache will be flushed as marked in red color. We try to improve locality of graph operations by making more use of common neighbors. First, we get the GK similarity between nodes. We then cluster the node pairs with high similarity and schedule nodes in the same cluster concurrently. As illustrated below, the locality can be improved through reordering. The irregularity of graph data then leads to workload imbalance with large variance in the number of neighbors, which then determines the center node's computation workload. Instead of distributing tasks in center node granularity, in our design, we group the neighbors of each center node according to the number of neighbors. A group size is set in advance, and then each group is assigned to a computing unit. The computing units in charge of tasks of the same center node will use atomic operations to update the results concurrently. The second optimization is data visible range adapter. It tackles the mismatch between stages in fine granularity, fusing the kernels and reducing overhead. In DGL implementation, the complex dependence between stages is tackled in coarse granularity, which then lead to large overheads in intensive function calls, as illustrated below. Our goal is to share the data in fine-grained way between stages to fuse the kernels and reduce the overhead. We firstly use data visible range to define the problem. Data visible range describes in what scope of threads a data item is visible to. In GPU, the data can be thread private, visible within WAP, visible within thread block, or global. In the right figure, the data in stage 1 is thread private, and data in stage 2 is shared within thread block. To reduce the number of function calls, we need to solve the mismatches between stages. We use data visible range adapter to solve the mismatches between stages. The adapter is a code snippet sharing data between stages in order to solve the mismatch. We find out the minimum data visible range required across two stages. Then it shares the data within the minimum data visible range. This slide introduces the detailed implementation. If the minimum required data visible range is warp, warp shuffle is used to share data within warp. Warp shuffle is a GPU primitive that transfers data between threads in the same warp. If it is within the thread block, shared memory is used to share data. Shared memory is a buffer that is visible to all threads in a thread block. Global dependence can only be tackled by launching a new kernel, which has an implicit global barrier. And graph operations will introduce global dependence, because computation for the center node will wait for all its neighbor nodes' data to be ready, and the computation for center node is assigned to different computing units. However, we can use the linear property for some of GNN operators, such as multiplication and division, to change the order of computation in order to merge the operations that leads to global dependence and to improve the parallelism. GAT is used as an example. The formula is the original computation, which is computed in the following computation graph. The green parts are the graph operations which have global dependency afterwards. There are two global dependencies, so we need two global barriers. However, the formula is equal to the right one. The division is postponed due to the linear property of the division and multiplication. And in the new computation graph, the multiplication and two graph structures can be computed in the same kernel with only one global dependence. The global dependence is postponed and reduced, and the parallelism is improved. The third optimization is sparse fetching and the redundancy bypassing. We can bypass the redundant data movement and transformation when performing the neural operations by graph structure. The following figure shows the implementation of DGL as introduced before. There are redundant data movement to form the dense matrix, and there are redundant transformation at every LSTM cell. In our design, the redundancy can be bypassed. First, without performing the transformation every step, we pre-transform the feature matrix before all LSTM cells. Moreover, the data movement can be bypassed using sparse fetching. Every LSTM cell will fetch from the pre-transformed feature directly from the transformed feature matrix. With all the optimizations, we further optimize the overall performance by auto-tuning. The inputs of GNN has various characteristics. For example, the graph structure and the feature length. There isn't a way that is always the best. To solve this problem, we use auto-tuning to choose the best parameters and implementations. In task scheduling, we have the parameters of locality-aware reordering and the group size of neighbor grouping to tune. In data visible range adapter, we have different implementation choices. And for general GPU computing, we can change the thread block size, which is also essential to the overall performance. At last, I will show the experimental results that demonstrate the effect of our optimizations. This figure shows the speed up over DGL of the different frameworks on GCN. The bars include the framework of DGL, PYG, ROC, and our implementation. Among them, the green bars show the performance, the speed up of our implementation. Our implementation is 1.81 over the best of other 3 frameworks. Some of the PYG and ROC data is invalid due to out of memory. We show them as 1 in the figure. This figure shows the performance on GAT, as GAT is a more complex model. Our implementation and optimizations can lead to much larger improvement. It is 15.5 over DGL and 38.6 over PYG, which suffers from being out of GPU memory on some large datasets. RLC has no support for GAT. In GraphSage LSTM, which performs neural operations by graph structure and has intensive computation, our implementation can still get 1.37 over DGL, while PYG and RLC do not support. To conclude, our work helps understanding the performance gaps in existing frameworks, which includes the graph-related performance gaps, such as locality and workload imbalance. GNN also introduced the combination of the graph structures and neural operations, which is the special complexity of GNN. It then leads to the intensive function calls, redundancy in performing neural operations by graph structure, and the inefficiency of variant feature layers. We then bridge the performance gaps with task scheduling, data visible range adapter, and sparse fetching and redundancy bypassing. According to our experiments, our optimizations can lead to 1.81, 15.5, and 1.37 improvement on GCN, GAT, GraphSage LSTM respectively over state-of-the-art. That's all for my presentation. To find more detail, please refer to our people paper, and the code is also open sourced at GitHub. Thanks for listening.